So we're at the last section of the notes here on the periodic table, and we're talking about the trends in the periodic table. So we saw how the periodic table was arranged, and we saw the scientists that got us there, and we figured out where metals, nonmetals, metalloids are, and we're starting to kind of figure out how to navigate this table. Okay, we're trying to basically decode it. It's been encoded, and now we're trying to decode it. And thankfully, you guys have the reference tables to kind of help you out too along the way. Okay, so the first term we're going to look at is atomic radius. This is going to be found, or radii, this is going to be found on table S. Okay, so most of the stuff that we're going to talk about is going to be found on table S or on the actual periodic table itself. So this is how we measure it. It's half the distance between two adjacent atoms in a crystal. We're noticing though the pattern, okay? The pattern on the periodic table is as you go from left to right in a period, there's a repeating pattern of decreasing atomic radius. So that means the atomic radius is going down. So we're seeing that the atom is actually getting smaller as we go from left to right along the period. Okay, kind of strange if you're thinking about it, because as you're going from left to right in a period, you're increasing the atomic number. You're increasing the number of protons, you're increasing the number of electrons, and you're also increasing the number of protons as we go, neutrons, excuse me, as we go along. So oddly enough, though, you're seeing that instead of the atom getting bigger as what you would assume if you're adding stuff, it should be getting bigger, we're finding that it's decreasing. And there's, again, particular reason why this exists. So why does this trend exist? Metals are larger than nonmetals. Okay, great. So again, it's getting smaller as we're going across to the nonmetal section. Okay, so across the period, the valence electrons are all at the same energy level, but the number of protons in the nucleus attracting them increases, making them smaller. So what we're seeing is an actual pull between the protons and the electrons. As we're adding more, that pull is greater, and it kind of squishes them in together and makes that radius smaller. So here we go. Lithium over here, group 1, all the way over, we're noticing a trend that's getting smaller, okay? As we go across the period, remember periods are these horizontal sections here, okay? As we're going across the period, it's getting smaller. How small? These are actual measurements in an angstrom. Okay, so again, what's interesting to note why this trend occurs is because we have now a greater attraction between the protons in the nucleus and the electrons in the shells. As we go across, we're adding more protons, adding more electrons, and now just the pull is just getting stronger. It's like taking a weak magnet, adding more magnets to it, and now turning it into a stronger magnet. We have a greater pull now. Okay, so this is actual visual diagram of what you can see. So in your lithium, you could see the distance, just, relative, of course. 3 protons to the nucleus, 3 electrons on the outside. Wonderful. Now, let's take a look at beryllium. Beryllium's got a little bit more. One more. Note the pull now in each direction now is getting a little smaller. Okay, you can see a slight difference. Let's take a look at boron. Boron, we're going to notice, jumps up to 5. And just take a look here at the distances. Now we have 3 valence electrons pulling in there too with those protons. Whoop. And now we've effectively shrunk the atom. So note the difference. Less out there to be pulled. A little more. And the greatest of this section here. Okay, so here you go. This is your chance to shine. Example number 9. Order the following elements by increasing atomic radius. Okay, so 2 ways to approach this question. 1, you remember the trend that we just talked about. 2, you forgot that. Take a look at your reference tables on table S and just take the time to find each element and put them in order in increasing number of the atomic radius. So the smaller number goes for K, excuse me, not for K, but goes for this direction here, and then the bigger value would then go into the opposite to the right. Okay, so increasing atomic radius. All right, so give that a shot. And I'll wait. All right. So if you take a look at just the trend that I showed you before, those that are on the metal side, they're going to be larger. So those on the left are going to be larger than the ones that are on the right, the non-metal. So actually in this example, it was not done on purpose, but they are actually already in order right now as increasing atomic radius. So potassium is your metal. He's going to be all the way to the left, and then GE, and then BR. And if you didn't believe me there, if you took a look on table S in your reference table, it should have got you to that answer as well. All right. So in a single group, so now we're going to talk about groups. So going down the periodic table by group, so the vertical sections. So in a single group, each atom has more inner level electrons than the preceding. This shields them from the nucleus, reducing the force of attraction from the nucleus. So basically what that means is as we go down a group, what you guys are going to notice is the atom actually gets bigger, which makes sense. You're adding more electrons, you're adding more protons. However, you're adding the electrons now. We're gaining another shell as we're going down the group. We're gaining another shell. Okay, so we're adding another level. And what that's doing is instead of it getting smaller like we saw as we went across the period, because we were adding more, the force now is greater. Now as we go down the group, we're not seeing that trend because we've added a new layer, a new level, and what's happening is the previous ones are shielding the distance between the electron to that proton. So instead of that pulling happening, we actually have shielding happening. So quite honestly, the way you could either think of this too is you're just adding another layer. You're adding another ring. And if you remember drawing the Bohr models, you had to add another circle, make a bigger circle going around. And quite simply, just that adding of that level, yes, the shielding is going on, but that too, because of that adding of the level, is making the atom bigger. Okay, so this makes the atomic radius increase from the top to bottom of the group. So this is basically the shielding effect. You could see that in this outside valence electron shell that we added, that's new, that would be your new circle going around. It's being shielded from the proton in the nucleus by the previous levels. So that's what I tried to explain in the previous slide. Okay. All right. So again, these are the trends that we are just kind of illustrating. It's going smaller as we go across. It's going bigger, getting bigger as we go down. So down each group, it's getting larger. As we go across, it's getting smaller. So here we go. Here's your chance. Order these elements by increasing atomic numbers. So small number to the left, bigger number to the right. Why does this trend occur? Okay, so give you guys a minute to do that. Oops. Okay, so which one is going to be where? So you could take a look at your table S to figure that out, or you could take a look at the trend that we were talking about before. So we have cesium, sodium, and rubidium. Cesium, sodium, and rubidium. So cesium is down here, sodium, and rubidium. So they want to know how is it getting bigger? Cesium, or basically order them from small to big. Cesium, rubidium, sodium. Okay, so they're in the same group, so you need to know how that trend works. And we said the trend works is that it gets larger as we go down the group. So cesium clearly is the largest one here, if you guys can see that. Rubidium comes into second place, and then sodium is the smallest. So if we're doing this in order of increasing atomic radius, then we have to do sodium first because he's the smallest. And then we go to rubidium. And then we would end with the biggest one on this list, cesium. Okay, and then we talked about why this trend occurred. It's due to shielding. As we're adding an extra layer, that layer is now shielded from the protons in the nucleus by the previous levels. And because there is some shielding happening, the attraction from the protons and the electrons are not going to be great. To make it smaller, indeed, it'll get larger.